Hi all, welcome to video lecture number 2 on strength of materials. In the beginning of this lecture,
we will try to recall what is strength of materials and how it is different from laws of mechanics. In structural elements such as bars, beams, shafts, cylinders, etc., we can find support reactions which are resulting from the applied forces using engineering mechanics or laws of mechanics. But suppose I consider a bar like this. It is fixed here, let us say. This end is fixed, and when I apply a load like this of some magnitude, from laws of mechanics I can calculate what is the reaction here. Reaction will be opposite to this load like this, and reaction magnitude will be equal to P. So this I can easily find out using laws of mechanics. But what is happening inside this material, inside the bar, how the bar is responding, all that I cannot analyze using laws of engineering mechanics, for which I have to use strength of materials. So while transferring the forces from the point of application to support places where resistive forces are developed, how it transfers, and during the transformation the material undergoes a deformation. For example, in this case it stretches like this, the length of the bar will slightly increase, so bar undergoes deformation. So this effect is studied under strength of materials. So basic laws of mechanics are also used here, but along with that we will observe how resistive forces are developed inside the material and how this material will respond to the applied load. So basically this strength of material is an interdisciplinary subject which is used by civil engineers, architects, use these concepts for designing trusses, beams, etc. of buildings and bridges. And aeronautical engineers need this for design of components of aircrafts, and many other engineering disciplines like mechanical, chemical. These engineers must know strength of materials for the design of machineries, pressure vessels, and other components. And apart from these disciplines, you also have mining engineers, metallurgical engineers, electrical, electronics, etc. So all disciplines use this subject. That is why this is one of the fundamental subjects. Now it's a core subject for mechanical, aerospace, civil, and IEM branches. Different types of loads that we come across. Different types of loads can be classified based on how it is applied, what nature load has, the magnitude or distribution of the load, and direction of load. Based on all these, you can classify. The first classification, it is based on the way in which load is applied. So based on this, you can classify it as gradually increasing load and suddenly applied load or impact load, and dynamic loads. Dynamic loads means the load magnitude will vary with respect to time. Load is a function of time. Loads can also be classified based on way in which it occupies on the structure. And in this classification, we come across point loads or concentrated load. Second one, distributed loads. In distributed loads, you have different types: UDL, uniformly distributed load; UVL; and trapezoidal, a third type of classification. Based on the direction, it is classified as direct load or normal load, which can be either tensile or compressive. And second category is tangential load, or it's also called shear load. Now we will talk about certain definitions. So let us understand certain terms which are very essential for understanding strength of material. First of all, what is strength? So whenever we talk about material properties, we say that some material or part is stronger than the other, or we try to compare two materials and say this is more safe, it has more strength. So basically, strength is the capacity of the material to withstand the action of external loads without exhibiting any type of fracture or failure. So any component, when it is designed, it is intended for doing certain function. So if the component or part, if it fails to perform its function, then it is a failure for us. So we say that the component is failed. So what is the capacity of the material to withstand the load and perform safely? That is called strength. When we have a beam like this, if I apply some load here of, let us say, 10 Newton, it undergoes deflection like this. This is the deformed shape, and this is the maximum deformation. I'll call it as Y max. But if I make this beam little longer like this, here I'll apply the same amount of 10 Newton. This also undergoes similar pattern of bending, but the deformed shape will have Y max. This I'll call it as Y max 2, this as Y max 1. So obviously Y max 2 is greater than Y max 1 because this length of this beam is more compared to the first case. So we say that first case it is more stiffer than the second case. So ultimately what we are comparing between these two cases is the deformation. So if the material or component deforms less, it is more stiffer. So stiffness is the capacity of the material to undergo lesser deformation. So it is measured as K is equal to F by delta, where F is the load, delta is the deformation, and K is the stiffness. So this is the mathematical expression for stiffness. It is load per unit deflection. The third definition is called elasticity. When we compare two materials, we say that this is more elastic compared to the other one. So especially when we use rubber materials, we observe that after the deformation, if I remove the load, the material will regain its original shape and size. That property is called elasticity. So it is a property by virtue of which material undergoes deformation and material regains its original size and shape after the removal of load. You have seen such materials. For example, rubber band, if you deform it by stretching and immediately after removing the load, it goes back and it takes the original position. So that is a property called elasticity. All materials will have certain amount of elasticity. None of the material in this universe is perfectly elastic, means it will not regain its original shape and size completely after the removal of load. But the difference amount may be very, very small. So in many analysis, we assume that the material is perfectly elastic and we do analysis. Fourth definition is plasticity. See, material regains its original shape and size after the removal of load. That is the definition for elasticity. If I say that material retains its original size and shape after the removal of load, then it is plasticity. If you take chocolate, if you bend it, if you apply load like this, it will undergo deformation like this, permanent deformation, right? It will not come back. That is the property called plasticity. Again, no matter is perfectly plastic also in this universe. And this plasticity property will be important for certain mechanical engineering applications. For example, in the machining process, the material undergoes plastic deformation. In certain processes like sheet metal, you would have worked on sheet metal workshop. So when you bend the sheet metal using some tools, it's a permanent deformation. There is a plastic deformation. Then the fifth definition is called isotropy. Actually, isotropy can be in terms of chemical composition, in terms of optical properties, in terms of electrical properties, etc. But when we talk about isotropy in strength of material, it is always with respect to mechanical properties. So iso means similar or same. So same properties in all directions. So same mechanical properties in all directions. In a material, if the mechanical properties are same in all directions, then it is called as isotropic body. The material properties can be different in different directions. For example, in case of wood, you would have seen wooden blocks like this. If this is a wooden block, the fibers of the wood will be distributed like this. So if you take a specimen out of this, or if you make some component bar out of this, that bar will have properties different in this direction and this direction, because the distribution of this material is not same in all directions in case of wood. So wood is actually an orthotropic material, but almost all metals and alloys are isotropic. But if you take example of wood or some composite material, laminated composite or anything, the properties may not be same in all directions. So in those cases, we have to consider them as orthotropic. Orthotropic is a case of anisotropy where properties will be same in three mutually perpendicular directions. Means along x direction, if you measure, the properties will be same. Anywhere you measure, it will be same. Along y direction, it will be different. So like that, three mutually perpendicular directions, the properties will be different. That is called orthotropy. Any doubt?
No, sir.
No, sir.
Okay. Then the sixth one is called homogeneity. Homogeneity means the material is continuously distributed in a volume. For example, if you take a component such as bar, the material is continuously distributed throughout its volume. If there is a small crack or a void, then this material cannot become a homogeneous body. Because of this crack or void, the properties will not be same, and that affects our analysis. So if we can assume that material is continuously distributed, even a small volume can be taken and enlarged for our analysis. We can analyze what are the forces acting on that volume, etc. So homogeneity is also important. The basic idea here is composition is same throughout. Next, we'll try to understand what is Saint-Venant's principle. Take example of a bar like this. If I subject this to a load like this, axial load, let us say of magnitude P, how do I apply this load practically? I can show a diagram like this and say that ends are loaded with P, tensile load. But practically, if you take a pen and try to expand it, how you have to apply the load? You have to grip at the ends and try to expand. So in the laboratory also, if you want to test this specimen, there will be a shackle like this. There will be a shackle which holds the specimen at the end like this, on the other end also, and then that shackle will be fixed onto some other part, and that part will be hydraulically loaded. You will understand this loading principle in MSM lab because you will be conducting tensile test and compression test there. Right now you understand that it will be held with some device and it will be pulled apart, then only it will be loaded like this. Now what happens when you load like this? The distribution of internal forces at the center, if you look at, it will be uniform like this. At the center, the distribution of force will be uniform like this. But if you take the distribution of internal resistance at the loading point, it will not be uniform. It will be somewhat like this. It will be varying like this. So at the center, it will be perfect a rectangular variation like this, but at the end it will be somewhat like this, parabolic. If I remove this shackle and use some other means, maybe I'll drill a hole here, I'll drill a hole on either side, I'll fix a bolt here, I'll keep a bolt here, and bolt will have a hook like this, let us say, bolt will have a hook like this. And for this hook, I'll tag it to some hydraulic device like this. Then if I apply the load for this component, this is also a type of load. Same amount of load can be applied using this type of mechanism also. This is another way in which I can apply the load. For the same specimen, same amount of load can be applied by using a different fixing mechanism. So if I apply the same load P here, now at the center, you will get the same rectangular distribution only because you are applying the same amount of load, but the location where you apply the force, there you may get a slightly different force distribution like this. So this is slightly different from this because the way you are applying the load is different here. This is what is the principle that is given by Saint-Venant. So now I'll write the statement of this principle. Now you'll understand it better. At points away from the loading points, the behavior of material will be independent of the gripping forces or type of application, load or local effects. This is a statement. Now you go back to the same example. At points away from the loading points, I'm talking about this center. At the center, it is independent of the gripping forces, means the way in which you try to load the specimen by using some shackle or by using some bolt, by using some screw or by using some thread or whatever, If you apply the same load, you will see the same distribution of internal forces here at the center. So it is independent of the gripping forces or type of application of load or local effect. So local effect means what? At the end where you apply the load, there the distribution is localized, or it depends on the way in which you apply the load. So this is the Saint-Venant's principle of superposition in strength of materials. Now I'll take some example. I'll use the same bar example here. Okay, bar. So a load like this. Let us say I'll call this load as P1. At either ends, I'm applying a load of some magnitude P1. P1 can be anything. Let us say 10 kilonewton. I'm applying a load of 10 kilonewton for the bar. So how you expect this bar to deform for this load? Let us say it deforms like this. I'll show the deformation in dotted line. It deforms so much. So the deformation that is observed, I'll write it as delta 1. Now for the same bar, I'll try to apply a different load now. If I apply a load of P2 now, let us say 20 kilonewton. For P2, the deformation observed will be little more than delta 1. So I'll call it as delta 2. Now for the same component, if I apply the load which is equal to P1 plus P2, means if I apply 10 as a first case, 20 as second case, now it is 30. It becomes 30. 20 plus 10 becomes 30. So 30 kilonewton load if I apply on this, I will get a deformation delta 3 which will be equal to delta 1 plus delta 2. This is the principle of superposition. If I apply the loads individually, see, I'm applying load P1 individually, I got a deformation delta 1. If I remove the load P1 and apply the load P2, I got the deformation delta 2. If I apply them together, P1 plus P2 if I apply, I'll get a deformation delta 3 which will be equal to delta 1 plus delta 2. I'll write the statement now. The net effect of all the loads applied on a body in any sequence is given by the algebraic sum of the effect of individual forces of the body. The net effect of all the loads applied on a body means this one, delta 3. Delta 3 is the net effect of all the forces, means P1 plus P2. In any sequence, means you can apply P1 first or P2 first. In any sequence you apply, the net effect will be equal to the algebraic sum of the effects of individual forces. Means individual effect of P1 is delta 1, individual effect of P2 is delta 2. Why he is saying algebraic summation? The load can be compressive also. I am taking tensile load, means I am pulling the bar apart, so it is stretching. So stretching means tensile load. So both P1 and P2 I have taken as tensile. If one of them is compressive, then I should have taken delta 1. If P1 is compressive, then I should have taken the value of delta 1 as minus delta 1. So delta 3 would have become minus delta 1 plus delta 2. So that is why, depending on direction of load, you have to take the algebraic sum of the effect. Then that will be equal to the net effect of all the loads. Assumptions in strength of materials. In any of the strength of material analysis or formulation or problem, we assume certain things. So we will try to list those assumptions now. First one, all bodies are deformable and deformations are small. In engineering mechanics, when you wrote free body diagrams or when you calculated reactions, you assume that the bodies are deformable. But now, since we are interested in finding what is happening inside the material, we have to assume that the bodies undergo deformation, but deformations are small. If you take a large deformation or large deflection, then there will be a non-linearity between force and deflection, which has to be dealt in a separate set of equations. Second assumption, materials are perfectly elastic. Means if I load the specimen or a component and unload it, it regains its original shape and size. Third one, materials are isotropic and homogeneous. Isotropy means all the mechanical properties are same in all directions. Homogeneity means the material is continuously distributed throughout the volume. There are no voids or cracks. Fourth one, principle of superposition is valid. The net effect of the individual forces is equal to the total effect of the forces which are combined. So that principle will be valid for all our analysis. That is the assumption we make. Fifth assumption, we assume that Saint-Venant's principle also is valid. So these are the assumptions we make before doing any analysis. Now we'll try to define what is stress. I'll take an example like this. I'll apply the load like this. Now we know that P is externally applied load. But if you cut this somewhere here, if I cut the material and write this separately, here there will be distributed forces. These are called internal resistive forces. Internally, the material develops these forces. If similarly on the other portion also, if I separate the other portion, this is externally applied load P, but here there will be internal forces. There will be resistive forces developed like this. If I separate portion 1, this portion has to be in equilibrium. So when I apply load P here, there should be equal and opposite force distributed here. So this will also be equal to P. Then only this will be under equilibrium. Similarly, portion 2 also, if I separate, applied load is P. So opposite side, opposite phase will have resistive force of intensity P. These are called internal resistive forces which are developed inside the material. But our P is externally applied. This is internally developed. Why I have written this also P? Because mathematically they are supposed to be equal. For equilibrium, the forces has to be balanced. So internal resistive force is equal to externally applied load. Now coming to the definition of stress, the intensity of internally distributed force that resists external load. This is the definition of stress. It is the intensity of internally distributed forces that resist external load. So mathematically, stress is denoted by the symbol sigma. It is given by P divided by A. A is what? It is the area of cross section. If the load applied is P, if the cross section area of the member is A, then it is the ratio of P and A is called stress. You may ask, load P divided by A is pressure, no? By definition, pressure is defined as load per unit area. This is stress is also similar to that. But the only difference between pressure and stress is pressure is externally applied always. This is external. But stress is internal. It is internally developed in the material. Why we are using this P? Because internal resistive force is equal to the external applied load. That is why we are using that P.